Chapter 3, Evaluating Properties. We are going to learn key concepts in thermodynamics, including phase, pure substance, state principle for simple compressible system, PVT, surface, quality, enthalpy, and specific heat. We'll analyze closed system, applying the energy balance relations and using the thermodynamic properties of the systems. And we'll learn to understand TV, PV, and phase diagram or PT diagram. Also, we'll learn to use the thermodynamic property tables at the end of the textbook, and we'll introduce the concepts of ideal gas and the ideal gas equation of state. And this is a foundational chapter of thermodynamics, and you will need to thoroughly understand the concepts in this chapter. Let's get started with the section 3.1. A phase is a quantity of matter that is homogeneous throughout in both chemical compositions and physical structure. So we know that there are three phases: solid, liquid, and gas. For example, at room temperature and pressure, air exists in gas. And drinking water with ice cubes contain two phases of water, liquid and solid. And when the temperature of water is raised to the boiling temperature, liquid water changes into a gas or water vapor. A pure substance is a substance that is uniform in chemical composition. So it does not have to be a single chemical composition. It may be a mixture of various elements or compounds, and it can exist in more than one phase. For example, water with ice cubes can be regarded as a pure substance because each phase has the same composition. So water in liquid phase and ice in solid phase both have the H2O, same chemical composition. Fuel-air mixture is also considered as a pure substance as long as the mixture of the gases is homogeneous. Air consists of various gases including nitrogen, oxygen, argon, and carbon dioxide. However, air is homogeneous as there is no change in the chemical composition during a thermodynamic process. So air is also considered a pure substance. In this class, we deal with pure substances like air, water, refrigerant, and air-fuel mixture. Here is a question: can oil and water mixture be considered as a pure substance? It is not a pure substance as they tend to remain separate. State principle for simple compressible systems states the values for any two independent intensive properties determine the state of a simple compressible system. Consider air in a closed system. We'll need properties of a system to solve the thermodynamic problems that we are going to be working with. There are many properties for the system. So we can describe the state of the system using the properties such as temperature, specific volumes, pressure, internal energy, density, enthalpy. According to the state principle for simple compressible systems, we need only two independent intensive properties to completely determine the state. It is also called fix the state. Fix the state. So for example, we only need temperature and specific volume to define the system, or pressure and specific volume to define the system, or fix the state. So if you know the temperature and specific volume of the system, the rest properties may be determined. A simple compressible system describes a pure substance, and there is no effect of electrical gravitational, kinetic, and surface tension effects. Keep in mind that two properties are independent. So independent property describes that one property is changed while the other property is held constant. What is intensive properties? Intensive property is independent of the amount of mass. So temperature, pressure, specific volumes, density, specific energy, internal energy, enthalpy are the examples of intensive properties. Section 3.2 PVT relation. In PVT surface, pressure, specific volumes, and temperature are plotted in a rectangular coordinate as a three-dimensional surface. This is a PVT surface. There are single phase regions, solid in light blue, liquid in green, and vapor in yellow. Two-phase regions are located in between the single-phase regions. So solid vapor regions in pink, between solid and vapor. Liquid vapor regions in orange, between liquid and vapor. And solid liquid regions in dark blue, is between solid and liquid. So in single phase regions, pressure, specific volumes, and temperatures are independent. In two phase regions, pressure and temperatures are dependent. What that means is once the temperature is specified, the pressure is determined and vice versa. So the state cannot be fixed or completely determined by temperature and pressure alone in two-phase regions. However, state can be fixed by pressure and specific volumes or temperature and specific volume. And this is only for two-phase regions. The triple line here indicates three phases can exist. If you project the orange liquid vapor regions onto a pressure specific volume plane, we have a curve like this. This is a saturated liquid line that connects all the saturated liquid states. This is a saturated vapor lines that connects all the saturated vapor states. In thermodynamics, saturation indicates the mixture of vapor and liquid, or it implies that it is about to change its phase. The point where saturated liquid line meets saturated vapor line is called critical point. The dome-shaped regions by the saturated liquid line and saturated vapor line is called the vapor dome. The state principle for simple compressible systems states two independent intensive property can fix the state. So we can project the PVT surface onto PT plane and PV plane and TV plane. So we can easily read and understand the variations of properties during the phase change process through the three property diagrams. So let's take a look at each diagram. The pressure temperature diagram is also known as a phase diagram. So we can see all three phases separated by three lines. That's solid, liquids, and vapor. The line indicates two phase regions. For example, the point here presents a two-phase mixture at this particular pressure and temperature. At the triple point, three phases exist at equilibrium. The temperature of water at triple point is assigned to be 273.16 Kelvin, and the pressure is 0.6113 kPa, kilopascal. Let's see TV diagram, temperature and specific volume. You may be familiar with TV process for water, temperature and specific volumes. Consider a closed system with water, and it has a very light lid. Initially, water is at atmospheric condition and the lid is free to move. So we boil the water. This is fire. During the process, the pressure remains constant. It's atmospheric pressure. As the temperature of the water increases, water expands and the specific volume also increases. At some point, water reaches 100 degrees Celsius and water starts to boil and vaporize. The phase change from liquid to vapor takes place. This is saturated liquid. The liquid is about to change its phase and it is about to vaporize. The volume of the system increases as water vaporizes. During the phase change, the temperature remains constant until the liquid is completely vaporizes. At this point, the system only contained water vapor. This is saturated vapor. The vapor is about to change its phase. At the saturated vapor, vapor is about to condense. As the mole energy is transferred, the temperature of water vapor rises. This is called superheated vapor. So all these processes take place at constant pressure. And this process will be reversed if the superheated vapor is cooled down back to room temperature. So imagine we add weights. If we add weights on the lid, the pressure of the water increases. By increasing the pressure of water, the process will follow a similar path. However, the water boils at higher temperature and the specific volumes of the saturated liquid is larger. And the specific volume of the saturated vapor is smaller. And the horizontal line that connects the saturated liquid and saturated vapor gets shorter as the pressure increases. We can add more constant pressure lines. At certain pressure, the saturated liquid meets saturated vapor. It is called the critical point. If the pressure is even larger than the critical pressure, there is no distinct phase change process. So this is TV diagram. Let's take a look at PV diagram. Consider a water enclosed system. and is under high pressure. It has several weights. And heat is transferred to the water, and the water temperature remain at 100 degrees Celsius. Initially, water is in a liquid phase. As we remove the weights one by one, the pressure decreases and volume increases slightly. And if we draw the process on PV diagram, as the pressure decreases, the volume increases slightly. When the pressure reaches the atmospheric pressure, it starts to boil until all the liquids vaporizes. The phase change from liquid to vapor continues at the constant pressure. As the pressure drops more, the specific volume of the water vapor increases. And this process was under constant temperature. We can draw another lines at different temperatures. This PV diagram shows the PV curves at various temperatures. The slope of the constant temperature line is downward. The pressure remains constant in the two-phase liquid-vapor region. In the single-phase liquid and vapor regions, the pressure decreases as specific volume increases. For temperature greater than or equal to the critical temperature, pressure decreases continuously as specific volume increases. So we took a look at three property diagrams. The property diagrams for water were used as an example, but the general shape of the property diagrams is similar for pure substances. Section 3.3, Studying Phase Change. So we are going to look at the phase change of a pure substance on the temperature specific volume diagram and introduce the concept of quality in the liquid and vapor mixture. Consider a closed system containing water. Assume the piston is weightless and free to move without friction. The system is under atmospheric pressure 14.7 psi or 1.014 bar. So water is initially in a liquid phase. On a TV diagram, it's at here, at point L. As the temperature is slowly heated under the constant pressure, it moves along the line from L to F. The liquid state is referred to as subcooled liquid or compressed liquid state. When the temperature of the water reaches 100 degrees Celsius, the water is about to vaporize, and the system is at the saturated liquid state. On the TV diagram, it is at point F, and the subscript F is usually used on the symbols of thermodynamic properties of saturated liquid. For example, VF denotes specific volumes at the saturated liquid state. UF, HF, or SF. So internal energy, enthalpy, entropy at the saturated liquid state. If the system is heated further, the amount of vapor increases in the mixture. So we want to know the proportions of the vapor and the liquid in the mixture to analyze the system. And the ratio of the mass of vapor to the total mass of the mixture is called quality, denoted by X. So the quality X is mass of vapor over total mass of the mixture, and total mass of the mixture is sum of mass of liquid and mass of vapor. The quality ranges between 0 and 1. At the saturated liquid, the quality is 0. The mass of the vapor is 0 at this point, or at point F, X is equal to 0. At the saturated vapor, the quality is 1. The system is completely filled with water vapor. So at point G, quality is 1. The point G, or saturated vapor, the system is completely filled with vapor. We use symbol G to denote the saturated vapor state. So Vg, Ug, Hg, or Sg. So specific volumes, internal energy, or enthalpy and entropy at saturated vapor state. Keep in mind that the quality is only defined in the vapor-liquid mixture region, or the vapor dome. So it is a thermodynamic property of the phase composition in a mixture. So we don't define the quality in the compressed liquid or superheated vapor region. The superheated vapor region is here, this line. So if the system is further heated from the saturated vapor state, the temperature of the vapor rises and the volume increases. And the state is called superheated vapor. On the PT diagram or phase diagram, we can see the three phases: solid, liquid, and vapor. If the pressure and the temperature go beyond the critical point, it is called the supercritical fluid. The supercritical fluid has a unique state with intermediate properties of the liquid and gas phases. We know that phase change from liquid to solid is freezing. The inverse of freezing is melting. The phase change from liquid to vapor is vaporization. Inverse is condensation. The phase change from solid to vapor, sublimation, and the inverse of sublimation is deposition.